Alright, so let's go back to the beginning and wrap up this statical classification. We started with that why do we have structural problems, and I linked it to that we have of many potential problems: collapse, partial collapse, and we also have modeling issues. There's a direct linkage between the mathematical stability of the system and the physical stability, and the beginning understanding of that is all in this fairly simple counting exercise where we count up the number of internal unknown forces and all of the reaction components that we don't know. And when I say we don't know, I don't mean that we could say, oh yeah, that's the trivial one, sum of forces in the x equals 0, and therefore, gee, I know that that horizontal component of the at that reaction has to be 0. Well, that's math. Even if it's trivial, that's math. So I'm talking about before we do any mathematical steps, what are the total number of internal forces that we don't know, and the reaction components. Those are the total number that we then need a series of equilibrium equations to help solve for. So n is these total number. So we end up with three different scenarios here. That if you don't have enough equations to be able to solve for those, then we're unstable in terms of the overall system. When a structure has total collapse, that is what has happened. That's something, if the building was okay before, but then it falls down, it was because something disrupted its ability to resist those the statical equilibrium requirements, right? Something broke, perhaps, right? If we have enough unknown components to satisfy all the available static equilibrium equations, we call it statically determinate if it is exactly equal. And if we exceed that, if we put more structure than we need there just for the requirements of static equilibrium, then we're statically indeterminate, and the amount of excess that we have is the degree to which we then are statically indeterminate. Now, it's not enough to have either just equal to or even exceeding. They also have to have, particularly the reaction components, must form a non-concurrent force system, else the system is geometrically unstable. You can also do some very sophisticated things internally in the structure too to cause geometric instability, but the basic one is associated with the reactions not being arranged properly. Right, so again, go back here. Collapse is entirely due to this situation where something happens in the structure and maybe some components up here break, and now we don't have enough anymore. Right? The other thing that can happen is that can happen in a local fashion, and we can end up with some partial collapse issues. Now, the modeling issues that arise are that when we try to create a computer model, we also must have one of these two situations, or the system is going to have, well, technically what's going to happen is have a 0 on the diagonal of the stiffness matrix, and then it won't be able to symbolically invert that stiffness matrix, and you won't be able to solve for the unknowns. What that actually means in real-world terms is that we've got an instability that ultimately is associated here. We don't have enough of something. And that can happen either because of the external constraints, or it can happen because of the way that we've arranged the members in the computer model, and to the degree that the computer model reflects the actual structure that we envision or have constructed, then that there's a direct one-to-one relationship between those things. Now, from a later on standpoint in this course, what this excess is going to mean to us and why we care about how much of the excess, well, if I've got 20 unknowns and only 18 equations, I've got to come up with exactly 2 more equations, and they're not equilibrium equations because they have to be independent equations. So we have to have 2 pieces of additional information, and that requires some effort to get to, and you'll learn how to do some of those things this semester.